We're in Chapter 2, Section 5, talking about the fundamental theorem of algebra. Sounds fairly important. And it is an important theorem, but it's also kind of like, it seems like we've discussed this before. We've discussed a version of this before. It's all about factoring and finding zeros. So now that we have discussed the complex number system, and reminder, the complex number system is the big umbrella. All of the numbers that we work with are in the complex number system. So this includes all the real numbers as well as all of the imaginary numbers. So that's the big umbrella that, here's my umbrella, that complex numbers covers. So now that we've talked about complex numbers, we can get more accurate about how we talk about the zeros of a polynomial function. So this is all about polynomials. The fundamental theorem of algebra, or the FTA for short, says that if f of x is a polynomial function, degree n, as long as n is greater than 0, so as long as the polynomial function is not constant, right? So it can be linear, quadratic, cubic, or higher. Then f has at least one zero in the complex number system. So what we said before was, given the degree, f of x has at most that many real zeros. So if x is quadratic, it has 2 zeros at the most. Here we're saying there's always a solution for at least 1 zero because we're talking about complex number systems. So that means that the zeros could be real or imaginary. We kind of build on that theorem. That's the fundamental theorem of algebra, but the linear factorization theorem tells you exactly how many zeros you're going to have. So if f of x, again, is a polynomial function degree n, and n is linear or higher, then f has precisely n linear factors, and therefore n complex zeros, because from each factor comes a zero, such that f of x can be factored into some coefficient a times x minus one of the zeros times x minus another zero, all the way out until you get to the nth zero. And again, those zeros, c1, c2, c sub n, those are all complex numbers. They could be real or they could be imaginary. Okay, so we're just going to go through a bunch of examples using these two theorems. On our AP Pre-Calc exam, I've been told that you're not going to have to cite any theorems. You're not going to have to say, by the fundamental theorem of algebra, blah, blah, blah. But you might be asked to write the linear factorization of something, and you need to know what that means. So write the linear factorization of a function just means factor the function. But in some places where we would have said prime, or where we would have stopped factoring on a speed quiz maybe, we're going to keep factoring this until we get it down to x to the first plus or minus a factor, or a zero, excuse me, for each factor. Okay, so what am I talking about? For example, x squared plus 36. If it were x squared minus 36, I would say f of x is x plus 6, x minus 6. Well, think about this. If you set this equal to 0 and you solve for x, I have a negative there. If you solve for x, you're going to get plus or minus 6i for x. So to write the linear factorization, I just say, well, there's a 1 in front of the x squared, so I don't have to put anything out in front here. It's going to be x plus 6i, x minus 6i. That's the linear factorization of the function. And I kind of did this in a backwards order. I kind of found the zeros first for this one, and then wrote the factorization. But to find all the zeros, that would mean that 0 equals x plus 6i, x minus 6i. So we're saying the zeros are plus or minus 6i. So whether you find the zeros first or you write the linear factorization first, it doesn't really matter as long as you know which is which. So factorization is with the parentheses. The zeros are the answers for x. Kind of the same thing on this one. Normally we would say x squared minus 11 is prime. It doesn't factor, but really we can break it down into its linear factors. Let's find the zeros first. So we add 11 to the other side. We get zeros of plus or minus the square root of 11. Those are the zeros. The linear factorization is g of x equals. There's nothing in front of the x squared, so I'm going to leave this as nothing in front of here. And then x plus radical 11, x minus radical 11. Doesn't matter which plus or minus you write first. And you can always check your answer by distributing your factors back together and seeing if you get back to the original g of x or f of x or whatever. And then in some cases, we can begin by factoring. So I'm not going to find the zeros right away. For this one, I'm going to factor first. I'm noticing a GCF that I can factor out, x to the third. Leaves me with x squared plus 9. And then just like I did x squared plus 36, I can factor x squared plus 9 now. It's x plus 3i and x minus 3i. Because if you FOILed that back together, you're going to get x minus 9i squared, which is x squared. I'm sorry, you're going to get x squared minus 9i squared, which is x squared plus 9. So here's the linear factorization. And then what are the zeros? X equals 0 from the x to the third. Now this is a repeated 0. It's technically repeated 3 times. This is like x times x times x. So 3 of the zeros are 0. And then also plus or minus 3i. Because I should have been doing this all along. We should have 2 zeros in the complex number system for a quadratic. We should have 2 zeros in the complex number system for this quadratic, and we should have 5 zeros in the complex number system for number 3. So if we check that, we got 2 zeros for number 1, we got 2 zeros for number 2, and if we recognize that x equals 0 technically could be written out 3 times because it came from a multiplicity of 3, then that is a total of 3, 4, 5 zeros. Before we get to the next section, where we start writing polynomial functions given the zeros, we have to know that imaginary and irrational zeros, they have to exist in these conjugate pairs. So if I know that 6i is a 0, then I also have to have negative 6i. If an irrational number, if x equals radical 11, I have to also have negative radical 11. So if you forget to square root and put in your plus or minus, you're supposed to have a plus or minus if you're solving for x squared equals anything. So anytime you get something imaginary, like x squared equals negative, or something irrational, x squared equals not a perfect square, you're going to get this plus or minus. Another example is like if x equals 2 plus radical 3, then x also has to equal 2 minus radical 3. If x equals 1 plus I, also has to equal 1 minus I. That has to be a 0. You can't just have the plus version or just the minus version of any one of those. They have to come in conjugate pairs. Okay, so armed with that knowledge, the next example says, write a polynomial function in both factored form and general form. So factored form is with parentheses, paying attention to an a value out in front. General form is, writing this out until you get to your final constant term. So foiling everything out. You need to start in factored form to be able to get the general form. So our first problem needs to be degree 4. And then we are told that it has zeros plus or minus 1 and 3i. So here's what I was just talking about. Imaginary zeros have to come in conjugate pairs. So also negative 3i must be a 0 as well. So it might help to write it like this. Zeros are x equals plus or minus 1 and x equals plus or minus 3i. So if you're trying to come up with factored form, you can say, well, let's just make it y equals If plus or minus 1 are the zeros, we can say x plus 1, x minus 1. If plus or minus 3i are zeros, we can say x plus 3i, x minus 3i. This is degree 4, right? If I were to FOIL this together, I have 4 of these x's. That would be x to the 4th. This would be the factored form of this problem. And on this one, it doesn't specify. You could, if you want to get creative here, put any coefficient out in front, as long as it doesn't have an x to make the degree different. You could put a 3 or a -1/2 or whatever. I'm not going to do that because I was also told to write this in general form. I've got to factor this thing together. I don't want to have extra math out here. So multiply the conjugate pairs together first. So like x plus 1, x minus 1, that's x squared minus 1. X plus 3i, x minus 3i, that's going to be x squared plus 9. And then you can multiply these together. X to the 4th, we're going to get plus 9x squared minus 1x squared, so plus 8x squared minus 9. So if I were to graph these two, factored form and the general form, they should be the same exact graph. All right, number 5 says we need to make a degree 3 function. This is something about end behavior. It's been a while since we talked about limits, but the limit as x approaches infinity, so as we head to the right end behavior goes down to negative infinity. The limit as x approaches infinity on the right goes down, the left side goes up. What does that mean? It means that our a value that we put out in front, it's got to be negative. It doesn't tell us what negative number to put in there, so we can put any negative number that we want. That'll be the last thing that we do. And then I'm only given 2 zeros, but it's degree 3. So remember, you're given a 0 of 0, x equals 0. And if you're given an irrational number like radical 2, irrational means the square root of not a perfect square, in this case, then remember, those come in conjugate pairs. So really plus or minus radical 2. And so if you're trying to solve for your function, let's make this one f of x. If x equals 0, it means we had a factor of x out here. Plus or minus radical 2, so one of them's x plus radical 2, one's x minus radical 2. And then remember, we've got to make this thing open down, so let's make it negative x out in front. So here's the factored form. To get the general form, you just need to start distributing. So monomials should be taken through last. So go ahead and always multiply conjugates together if you can, because they're easy to multiply together. X times x is x squared. Radical 2 times negative radical 2 is minus 2. And then distribute that negative x through. Negative x to the 3rd plus 2x. Again, if I were to graph this in y1 and this in y2, I should get the same exact graph. They should lay right on top of each other. 6 has one extra thing that we haven't had yet. So, okay, we're told cubic, so that means degree 3. We're given a 0 of 2 and 1 minus I. Remember, that has to have a conjugate pair. 1 plus I also has to be a 0. And then here's another thing. We're told that f of 1 has to equal 3. So we're given an actual function value. This is going to dictate what coefficient goes out in front. And we have to do this last. All right, so let's start building the factored function first. We've got, I'm going to call this one h of x. H of x is some a value, I don't know what it is yet, times x minus 2 times x minus 1 minus I times x minus 1 plus I. Remember, when you set up factors, it's always x minus the factors, so you need parentheses around the binomials. Okay, and then clean those up a little bit. So a times x minus 2. Let's make this x minus 1, distribute the negative, plus I, x minus 1 minus I. Okay, and then we're told to plug in f of 1 equals 3. Now, if we plug in 1 for x and 3 for h of x or 3 for y, try to solve for a, it's going to be weird because we have these i's in here. So let's work on getting this into its general form a little bit, and then we'll figure out a, and then we'll go back and write our final factored form. Okay, so you could slog through this and say x times x times negative 1, x times negative I, negative 1 times x, negative 1 times negative 1, negative 1 times negative I. So if you carefully do this and combine like terms, you'll get to the right answer. But I want to point something out. Anytime you have a 0 like this, that's a binomial, and you've got conjugate pairs, you're still working with conjugates. X minus 1 plus I, x minus 1 minus I. Remember the way conjugates work? It's just the first times the first times the first. So this is going to multiply to x minus 1 squared. And then the outside and inside are going to cancel out. So then you're going to do I times negative I. So minus I squared. That's the way that distributes. And then let's just leave this a times x minus 2 out here. That's helpful because it saves me a bunch of distributing. And I can clean this up easily. I squared is negative 1. So minus negative 1 is really plus 1 right here. Okay, so h of x is, we're getting somewhere with this, a times x minus 2 times x minus 1 squared plus 1. I'm going to stop right here because now I could like FOIL this out and combine, but I'm still trying to figure out a, and I'm in a pretty good spot to plug in when x is 1, y is 3, and start solving for that. So let me bring that work up here. H of x is 3 when we plug in 1 for x. I'll use my square brackets to distinguish. So I put in 3 for y. I put in 1 for x here and here. Now I've got a little bit of math to do. 1 minus 2 is negative 1 times a. 1 minus 1 is 0 squared times 1. So a is negative 3. All right, so that means I can finish my factored form. So here we go. Now I know h of x in its factored form is negative 3, x minus 2, and I'm going to write this version where I distributed x minus 1, x minus 1 plus I, x minus 1 minus I. That would be my factored form of that problem. If I want to get to the general form, I've got to keep working on this thing now. So I can say, all right, now I'm here. H of x equals negative 3 times x minus 2 times, let's go ahead and do this math in here, x squared minus 2x plus 1 plus another 1 because of that. This is negative 3 times x minus 2 times x squared minus 2x plus 2. Now, we don't save ourselves from a little bit of slogging, like multiplying this through, but this binomial times this trinomial is much better, in my opinion, than keeping track of trinomial times trinomial and with i's and stuff. I distribute constants through last, so I'm going to, I'm going to multiply together the x minus 2 times the x squared. So x cubed minus 2x squared plus 2x, and then distribute the negative 2 through. Minus 2x squared plus 4x minus 4. And then I'll combine some like terms. I'm really struggling for room here. So h of x equals, so we're going to have negative 3x cubed. Let's see if I can handle keeping track of this math here. Negative 3x cubed. And then for the x squareds, we have minus 4x squared times negative 3, so plus 12x squared. For the x's, we have 6x times negative 3, so minus 18x. And for the 4, that's getting negative 4 times negative 3 is going to be plus 12. Okay, so that is our h of x right there. Okay, that's the most complicated problem I could give you. You've got to remember about a conjugate, and you have a very specific point that has to be on the graph. So this means if we plug in 1, we should get 3. So negative 3 plus 12 is 9. 9 minus 18 is negative 9. Negative 9 plus 12 is 3, so that's a good sign. Anyway, that's as complicated as that could get. What else are we doing with these theorems? So now that we can completely factor and we can find all zeros, we should be able to find all complex zeros. So again, that means find all real and imaginary zeros given any polynomial. So the first thing is looking at it, can it just factor? Like, could this be on a speed quiz and you factor it right away? If so, assuming it's equal to 0, factor completely and solve. I'm going to make a note of that. Must equal 0 first. But most likely in this chapter, in this section of this chapter, you won't be able to factor it just by looking at it. So take a look at these. They don't factor by grouping because they're 5 terms, or they don't factor in any way that we've learned by grouping because they're 5 terms. So if it doesn't factor, you're either going to be given a 0 or you're going to be given a factor. So given a 0 is like x equals c is a 0 of the function, or given a factor is like x minus c is a factor. Then if that's the case, you can use polynomial division, and depending on what you're given, it could be synthetic or long division, depending on whether you're given a linear factor or not, to begin factoring the polynomial. If you're given multiple zeros or multiple factors, you'll need to repeat the polynomial division. So you might have 2 rounds if it's a degree 4, or 3 rounds if it's degree 5. And in the end, after you've done your polynomial division, you'll know you're finished when you get this thing down to a quadratic, because we can solve any quadratic using quadratic formula if we need to. So once we have all the zeros, we can write the completely factored form and find all the zeros, and that's our goal here. So let's look at some different scenarios. F of x is something degree 4. We're given that negative 1 and 2 are zeros of the function. So that means that even though I don't know how this factors right now, I know that x plus 1 must be a factor, and x minus 2 must be a factor. And then there's some other stuff here to make this x to the 4th. There's going to be some other quadratic to figure out. So this is where we can use polynomial division. We can either use synthetic division with negative 1 and 2 as our numbers on the outside, or we could FOIL together x plus 1, x minus 2, and do long division. So let's see. I'm going to show you the synthetic division here because we'll have to use long division on number 8. Okay, so it doesn't matter which one I start with. I'm going to start with negative 1. If negative 1 is a 0, remember, if negative 1 is a 0, we should be able to do synthetic division. I'm setting it up right now. And we should get 0 in this remainder spot. And by doing synthetic division, what we're doing is dividing x to the 4th by x plus 1. And so that's going to leave us with an x to the 3rd result. So that's going to get us closer to being able to solve. All right, so let's remember how this goes. You drop down the first number, and then you multiply and add, multiply, add, multiply, add, multiply, add. And this represents remainder, constant, x squared, x to the 3rd. It is beneficial to factor as you go, not required, but so far here's what we have. F of x we now know equals x plus 1, what we just divided by, given that 0, times x to the 3rd minus 2x squared minus 7x plus 14. The reason I say it's beneficial to write out your factorization right now is because this factors by grouping this result, but maybe we don't recognize that. So I'm just gonna make a note. Could factor by grouping. That doesn't always work though. So let's say we don't recognize that we could factor by grouping right there. We take the other 0 that we were given, which was 2, and we're dividing x minus 2 into the cubic that was left over. 1, -2, -7, 14. Drop down the 1, multiply, add, multiply, add, multiply, add. This is a remainder constant x squared. Remember, we're finished, or we're on our last step, I should say, if we get down to a quadratic, which we are. So here's what we have now. F of x is equal to the x plus 1 we factored out. And now we just figured out that this x cubed, this part of the function, is factored into x minus 2 because of what we divided by, times x squared minus 7. And x squared minus 7 gives us our zeros. We can factor that a little bit further. So the linear factorization of f of x is x plus 1, x minus 2, x plus radical 7, x minus radical 7. And if you're not sure on that last piece, remember you can find the zeros and then go back and write the linear factorization. The zeros are x equals -1, 2, plus or minus radical 7. Remember to include the 2 zeros or however many zeros they gave you as part of your answer. Okay, what about number 8? Number 8 is another degree 4. We're given an imaginary 0, so you don't want to do synthetic division with an imaginary number on the outside. And remember, if 2i is a 0, so is -2i. So that means that factors of y are x plus 2i, x minus 2i. And if I want to get rid of y's, not y's, if I want to get rid of i's, I can multiply these together. So I can say, okay, I know that x to the 4th, this polynomial here, is divisible by x squared plus 4, right? If I FOIL this together, x squared, 2i times -2i is minus 4i squared. So that means that I know that this factors into x squared plus 4 times some other quadratic that I have to figure out. Now I can't use synthetic division because I'm about to divide this x to the 4th polynomial by this x squared plus 4, and we can only do that if we do long division. So let's set up our long division. X squared plus 0x plus 4, placeholder so everything lines up nicely. We're dividing that into x to the 4th plus x to the 3rd minus 2x squared plus 4x minus 24. Okay, remember how long division works? We say, what do we multiply x squared by to get x to the 4th? We multiply it by x squared. And then you multiply x squared by x squared plus 0x plus 4. So that gives me x to the 4th plus 0x to the 3rd plus 4x squared. Subtract the whole thing. 1 minus 1 cancels out. 1 minus 0 is x to the 3rd. -2 minus 4 is -6x squared. Drop down the plus 4x, so you have 3 terms to line up. What do we multiply x squared by to get x to the 3rd? Plus x. So x to the 3rd plus 0x squared plus 4x. Subtract all 3 of those terms. X cubed minus x cubed. That first one should always cancel. That's how you're setting it up. -6 minus 0 is -6x squared. 4 minus 4 is 0x. Drop down the last term, which is minus 24. And finally, what do we multiply x squared by to get -6x squared? Multiply by -6. That becomes negative 6x squared plus 0x minus 24. It should leave you with no remainder because you were given a 0. You built this divisor based off of 2 zeros, so it has to divide perfectly into the polynomial you were given. What does this tell me so far? It tells me that I can factor y into what I divided by, x squared plus 4, times the quotient at the top, x squared minus x, plus x minus 6. And each of those are quadratic, and they can be turned into linear factors. X plus 2i, x minus 2i. This trinomial is x plus 3 times x minus 2. And the zeros are x equals plus or minus 2i, and negative 3, and positive 2. For this last one, we're going to use a graphing calculator. So notice I gave you this g of x. The directions are still to write out the factorization and find all the zeros. We're going to use a graphing calculator, but I want exact answers only, meaning if they're decimals, we really need their radical or a fraction version. I don't want rounded decimals. So first off, type the equation into your y equals. So this is x to the 4th. Oops. There we go. Minus 3x to the 3rd plus 6x squared plus 2x minus 60. I'm not sure what the zeros are, so I'm just going to zoom 6 to see what happens. If this is x to the 4th, I really just need 2 rational zeros that I can use either synthetic division or long division on. So that's what I'm looking for, zoom 6. So it looks like negative 2 and 3. I can verify that by going to my table. I'm going to second window because I remembered that my table was at a weird spot until it just started at 0. And second graph. Yeah, so 3 is a 0 and negative 2 is also a 0. Okay, so I can say from my calculator, I could see that x equals negative 2 and positive 3 are zeros. All right, now I have a choice. I can do synthetic division twice like I did in number 7, or even though these aren't i's, I can still FOIL them together and use long division like I did for number 9. So it really doesn't matter. I don't know what you prefer. I think I'm going to do the synthetic division. Why not? I think it's usually what most students prefer. We'll see what happens this year. Usually we like this because we can go through it kind of quickly. So see how you do on this. Remember, you're supposed to end up with 0 in the end there. I'm not going to take the time to write out what I have so far factored. I'm just going to do a second round of synthetic. Remember, you're just using this cubic result. You're not going back to the original. Otherwise, you'll be going in circles. And do not include the remainder because it's 0. You should get 0 in this remainder spot as well. Got this down to a quadratic. So here's where I will start writing the factoring so far. So far we've got it down to this. We had a 0 of negative 2, so one of the factors is x plus 2. We had a 0 of 3, so one of the factors is x minus 3. There's no number out in front here because it's a 1x to the 4th. And then our result was x squared minus 2x plus 10. Now that does not factor because the factors of 10 are 5 and 2. It's not going to give me negative 2 in the middle, but I can use quadratic formula to figure out what these remaining zeros are. Okay, so 2 plus or minus the square root of 2 squared is 4, minus 4 times 1 times 10, all over 2 times 1. 2 plus or minus the square root of, this is 4 minus 40, so negative 36. That's 2 plus or minus 6i over 2. That's 1 plus or minus 3i. So linear factorization. You're not finished when you get it to this point. Linear factorization means show me how this x squared factors. So now it's down to x plus 2, x minus 3, x minus 1 plus 3i, x minus 1 minus 3i. You can leave it like this if you want, or you can distribute the negative through. The only reason I would distribute the negative through is if I was supposed to get this into general form, and I'm definitely not going to do that because general form is the original. There's no need to go back and FOIL this all together. What are the zeros? The zeros are x equals negative 2, 3, those were from my calculator, and 1 plus or minus 3i. So you're kind of finding the zeros first and then going back and writing the factorization for some of these. It's sort of like I keep going back and forth between the two forms. But yeah, that's what that theorem is used for. So now we're able to find all of the zeros and we're able to factor any polynomial as long as we're given some way to find the first couple of zeros so that you can do synthetic division or long division for the rest. All right, if you have questions over this, please come to office hours or ask in class.